Right. So it's good, useful to remember the historical development of the idea of curvatures of surfaces, and as you know, for until about until 1915, essentially, geometry and non-Euclidean geometry and physics developed separately until we learned from Einstein that the geometry of space-time is non-Euclidean. So if you go back to Euclid, there was no curvature, plane geometry. This is a famous book, Elements. Then 1600s, Newton and Leibniz invented calculus, defined curvature for plane curves using second derivatives. So these are extrinsic curvatures. If a curve is bending in a plane, you can talk of its curvature, and that's formally defined in calculus. Then Euler introduced normal and principal curvatures. So somehow the idea of intrinsic curvature is coming, that a surface can have a curvature which is intrinsic to it and a normal curvature which comes from its embedding in a higher dimensional space. Then with Gauss, the real modern development starts. Define Gaussian curvature k equals k1, k2. If you have a two-dimensional surface, you can define principal directions along which the curvature is defined as k1 for one principal direction, k2 for the other, and the Gaussian curvature of a surface is given by this product. And this idea now becomes clear, it's very profound. Curvature is intrinsic to a surface. So we will not be interested here in curvatures that arise from embedding a surface in a higher dimensional space. Like if you embed a cylinder in 3D space, it has curvature because of the extrinsic curvature, because of the embedding, but it does not have any intrinsic curvature. A cylinder is flat, whereas a sphere has intrinsic curvature. And then comes the monumental work of Riemann, generalizing Gauss's concept of intrinsic curvature from two-dimensional surfaces to abstract higher dimensional manifolds, including three-dimensional space, any number of dimensions. And for us, as we realize later, it does not matter what the signature of the metric is. It can be plus, 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 plus Euclidean, or it can be plus, minus, minus, minus Lorentzian. Riemann showed how to describe curvature given the metric. Of course, we know curvature can be defined just given a connection. You don't need the metric. That generalization came later. And finally, with Einstein 1950, Riemannian curvature is utilized to describe gravity as the curvature of space-time. So we can, historically, curvature began as bending of curves and grew into the geometry of the universe. And this much for space-time geometries, but we know today that the same idea of curvature describes also the fundamental interactions, the strong force and the electromagnetic and weak force. That curvature is not of space-time, it is of this mathematical entity we call the fiber bundle, but maybe at a deeper level there is a reality to the fiber bundle also. It's not just mathematical. Modern research is focused on generalizing Riemannian curvature geometry to what are called non-commutative geometries. Your coordinates of this manifold, the x, y, z, t coordinates of the manifold now do not commute with each other. The coordinates have become operators or matrices. They don't commute with each other, something that I talked of in the earlier lectures. And could it be that such non-commutative geometries, the most important one of them is the so-called Alan-Cohn's non-commutative geometry, which is a very natural generalization of Riemannian geometries. Is this useful in quantum gravity? This is ongoing research. And the latest developments consist of generalizing so that not only is the geometry non-commutative, it's also non-associative. That is, if you have operators A, B, C, the coordinates have become operators. Let's say your x, y, z are now matrices. X is the product is now to be made such that these operators are no longer associative in multiplication. AB times C is not A times BC. Such geometries, this is very new, last few years, are known as non-associative geometries. They have a very intimate connection to the number system of octonions, because octonion multiplication is also non-associative. Are these going to play a role in unification of gravity and the standard model particle physics forces? Perhaps. It's definitely a very interesting thing happening, and this is all happening independent of string theory. So it's not that string theory is the only idea in unification. There is much happening outside as well. So if you look for non-associative geometry and octonions, you will find what is going on in the current literature. And if you are interested in such things, curvature, geometry, I think these are very interesting new ideas, new fields to work on. Okay. So we want to talk of curvature in the language that we have developed so far, differential forms. So I have just reproduced a slide from yesterday. The two Cartan structure equations introduce the connection 1 form and the curvature 2 form. The torsion is defined by this relation. If torsion is 0, this object is 0, and the exterior covariant derivative capital D of basis 1 form EA is given by this relation. So this is like the Christoffel symbol. Please remember, omega ABs are like the same objects conceptually as the Christoffel symbols. They tell you how basis vectors change under parallel transport. Okay. So this equation relates the exterior derivative of the frame EA to the connection 1 forms omega AB and the torsion tensor theta A. Exterior derivative now acts on vector valued 1 forms. This A labels a set of basis 1 forms, say A running from 1 to 4. It tells how the frame rotates as we move along the manifold and how this rotation is related to the torsion. The second Cartan structure equation, the curvature 2 form, is equal to the exterior derivative of the connection 1 form plus this wedge product of omega with itself, and this defines the Riemann tensor component. So today we want to justify in the next slide why this object is the Riemann tensor. We have been introduced to the Riemann tensor yesterday. Why this fellow defined like this, apparently in a different way, is actually the same object. What is this doing? If you try to visualize it, this is connection. Exterior derivative of the connection like derivatives of gammas, right? And this is antisymmetric. So if you remember the basic expression for the Riemann tensor, it involves terms of the form gamma times gamma, right? There are gamma gamma terms and there are gamma prime terms. So these are like gamma prime terms, these are like gamma gamma terms. So this is essentially the same thing as the Riemann tensor coded in a different language of a 2 form that we call the curvature 2 form, written in this calligraphic, or I don't know what scriptar or whatever. And you can write it in terms of components. The basis, you can write it in terms of the basis 1 forms. Any form can be, 2 form can be written in a basis like this, and the Riemann tensor R, A, B, C, D are the basis components of this curvature 2 form. This equation relates the exterior derivative of the connection form to the curvature 2 form. So we are differentiating the connection 1 form to get curvature. It describes how the connection itself changes, and this change is directly related to the curvature of the manifold. The torsion 2, so in these two Cartan structure equations, there are these constraints. if you apply the exterior derivative once more, you get these so-called Bianchi identities. We will see this in more detail today as we go along. The covariant exterior derivative acting on the torsion tensor gives you a term which is proportional to the curvature 2 form. If the torsion is 0, this reduces to the cyclic identity on the Riemann tensor, and this is the Bianchi identity that we are familiar with in general relativity. You know the Einstein tensor, it was introduced yesterday? Not yet, is it? R mu nu minus half G mu nu r, no, okay. So this, we will come back to this. This is the so-called second Bianchi identity. Okay, so we want to justify that what we, this definition is actually the Riemann tensor. So there is one simple way to try to convince ourselves. With this definition of the curvature 2 form, prove that parallel transport of a vector around a closed loop is proportional to the curvature tensor. I want to remove this. Curvature 2 form. So you did this loop transport yesterday? Yeah? That was done? Parallel transport around a closed loop. How does the Riemann tensor define then? Non-commutativity of covariant derivatives, is it? Parus, how was the Riemann tensor introduced? Huh? Okay, somebody at least please tell me. Because
it was done. So we took the second covariant derivative.
yeah, the non-commutativity of the covariant derivative. The loop transport was not done, is it?
No, not the loop.
Oh, that's very basic. I took it for granted. See, the one very visual way to introduce the Riemann tensor is to take a closed parallel loop, say imagine a parallelogram A, B, C, D. I have drawn this here. Something like this. Take a closed loop A, B, C, D, okay? Say, imagine a loop or a parallelogram. I'm going to take some vector V, parallel transport it along X, then from B parallel transport it along Y, from C parallel transport it along minus X and along minus Y back to A. When you do such a parallel transport of a vector V along this closed path, when you come back, the final vector at A, compare it with the initial vector at A, that change is proportional to something which is the Riemann tensor. It involves two derivatives of gamma. I must be having that expression somewhere. Right. This thing written in the first line, this you saw, right? And this was obtained from the non-commutativity of the covariant derivative. If you take a vector around a closed loop, the change in the components of that vector is proportional to this fourth rank tensor, which is also the Riemann tensor. So you can either define it from non-commutativity of derivatives or change in vector components when you go around a closed loop, etc. There are other ways to also do this. So you get some hang of this, no? I had assumed that this would have been done, and I was going to show the same result using one forms, but to take this as the basic derivation then. 4 infinitesimal parallel transports around a closed loop of a vector V. Let x and y be two vector fields spanning an infinitesimal parallelogram, like in this figure. Let V in basis VA, EA be the vector field we want to transport around the parallelogram. These components are in the orthonormal frame EA. Omega AB are the connection forms, and the curvature 2 form is defined like this. Okay, so we want to show when you make a parallel transport around a closed loop, a change in the vector is proportional to this 2 form. We want to compare the final and initial values of V after being transported around the loop. First, move along x, yeah, like here. Second, move along y, like here. Then move along minus x, x, y, minus x. Then finally along minus y. Track the changes in the components VA in the moving frame EA, and on the next slide we do the 4 parallel transports. Transport V along x from point A to point B. Now we know that we are doing the torsion free case. We can do the case with torsion also. This definition of Riemann tensor that I just showed you in terms of gammas holds even when torsion is present. The non-commutativity of covariant derivatives gives you same expression, and if it depends on the metric, the gammas will be determined by the metric, the symmetric part of gamma. But the antisymmetric part of gamma can still be present even if there is a metric, and that will depend on the torsion. So I will show those expressions slightly later. Okay, so when I transport VA, so the starting point, the vector is VA. The change in the components of VA, I didn't show the vector, that is given by this expression, where omega AB is acting on the vector x. Okay, there you can put an arrow on top, vector x. A form acts on a vector. Omega AB is a connection one form, A and B labeled different one form. This acts on the vector x to produce a number, and the change in VA when you come from here to here, okay, that is given by this fellow. So take this vector now. This is my vector. What is the vector at the point B? It is, I am transporting A. So the vector at point B is whatever it was at A minus this change. Okay? Do you get this? Transport the updated vector along Y and expand to second order. That is, I am now going B to C. So change in the vector at B. This is the vector at B. Change in the vector at B as I move along Y. What will be the change in VAA? That is given by this. That is this fellow. Right? Then there is a change because you have to make a change in omega, which is this term. Delta y of omega AB, delta y of omega AB is partial derivative with respect to y of omega AB into epsilon, because that is the variation along y, okay, and this term will just stay multiplied by VBA, this fellow, and then you have to still do a variation of VBA, which is given by omega BC. So variation of VBA. So omega AB of y, I have I think there's some change of notation. This omega I will keep as it is. Okay. There is some notational mix here. Let me correct it. Omega AB at x, at omega AB at x, omega BC at y. Right, this is correct, this is correct. When I do a variation of delta VBA, I will get this term. Do you get the hang of this? Right, so to repeat, when I vary this, I will get a variation of this VA. I will get two terms from here. They are going to be order epsilon square. Okay. So do the same thing now. Transport the vector from C to D by the same logic, and then from D back to A. I will not go into all the steps. I hope you get what I am doing. Add all the 4 changes. So there are 4 changes. First here, second here, third here, fourth here. This will tell you the thing on the left hand side. It is called a holonomy. It will tell you how much did the vector rotate when you went from A to B, B to C, C to D, and D back to A. And you add all this up. This is what you get. 2 terms which are like gamma primes. Gamma prime, and 2 terms which are like gamma gamma. It's the same structure as the Riemann tensor. This, by definition, is this is the definition of the curvature 2 form. Right, this is the curvature 2 form. This fellow, this compact fellow, is the same as this object. So if you just sit down and do this, you will get the change in the vector is proportional to this 2 form. So this 2 form is acting on x and y, and the change in delta, the VA, is proportional to the vector itself. Okay? All right. So then
So the whole idea is you start from one vector,
yeah,
complete a closed loop,
yeah,
back and compare these 2 vectors.
yes, yes.
So we can do it with shapes with sides more than 4, right? Like
Yeah. No. Very good, very good. We do this for surfaces. This is an arbitrary surface. So this, even if it's a higher dimensional space, say 10 dimensional, think of it as a collection of planes. So this is some arbitrary surface. You could have projected it if you want on some your coordinate plane. You could do that, but you have to take a surface. So what is real good question? What is happening is Gauss define curvature of a surface, intrinsic curvature of a surface. 1 by rho 1, 1 by rho 2 are these principal curvatures, and then you get 1 by rho 1, rho 2. What Riemann is showing, if you have a higher dimensional space, you can think of it as many surfaces stacked in different directions. For each surface, you can think of calculating its intrinsic curvature, but the curvature of this whole space is defined and described as by more than one number. Gauss needs only one number for a 2 surface. For a higher dimensional space, which you can call a hypersurface, you need more numbers. But you do it for surfaces. Right, and this looks convincing enough that this object is curvature and its projected components on a basis is the Riemann tensor. We see more evidence for this as we go along. So by this loop, transport of a vector around a closed loop, I've tried to justify that what you get in the end is nothing but the conventional Riemann tensor. There you transport a vector and you calculate the change using gammas, Christoffel symbols. Here you calculate the change using connection 1 forms. And this expression is true in general, even if there is a torsion present. Okay, so now let's do a couple of examples to compute the Riemann tensor using this expression. Okay, using orthonormal frames. The surface of a 2-sphere is here, so we are doing it for a 2-sphere now. Orthonormal frame, this we did yesterday. E1, the basis one form is r d theta, E2 is r sin theta d phi. Okay? The first Cartan structure equation, so we assume now torsion is 0. So dEA plus omega AB wedge EB is 0. The first Cartan equation. So put A as 1. dE1 is a d of r d theta, and this is 0 because my r is a constant. I am on a 2 sphere. So dr vanishes, d2 d square theta vanishes, which means omega 1 2 E2 is 0. We did this yesterday. So omega 1 2 is just some function of E1 or E2. Should be E2, no? Because if this has to vanish, omega 1 2 should be proportional to E2. So let me correct that also. Omega 1 2. Why is it E2? Huh? Others won't be 0, right? Only when omega 1 2 is proportional to E2 will this thing vanish. So this function, so it is some function of E2. Now do dE2. E2 is here. D of this, r is a constant, and d r cos theta d theta d phi, and d square of phi will be 0. So okay, and I can write this in terms of E1 and E2, because my d theta is E1 by r, d phi is E2 by r sin theta. So r square 1r cancels, so you get cot theta, etc. Okay, and so this is my dE2, and from the first Cartan equation, dE2 is also equal to minus omega 2 1 E1. So put that here, and that immediately tells you that omega 2 1 has to be equal to, so where do I get that? By comparing this and this. dE2 is this, omega 2 1 is this, and this relation has to be true. So put expression for dE2 here basically, right? So you get by comparing this and this, you get that omega 2 1 is here, omega 1. So this much we did yesterday. Now we can compute curvature. Computing the curvature from the second Cartan structure equation, which is given here. Omega 1 2 I know, that's omega 1 2 I have calculated. It is cot theta by r something, and I can write it like this: cot theta d phi. What did I do here? Let's check it a bit carefully. E2 is r sin theta d phi. R sin theta, r cancels, and this huh? This is cos, no? Yeah, cos theta over sin theta d phi. No, substitute for eta, for E2. E2 is r sin theta d phi, r cancels, so this should be cos. Yeah. So okay, anyway, we can this is correct. Cos theta d phi. So I know omega 1 2 is cos theta d phi. I need d of omega. Do the same thing again. D of cos theta d phi is minus sin theta d theta wedge d phi. Write it in terms of E1, E2. This object will vanish. You can easily check that this object is going to vanish, because if I put C as 1, the first one is 0 because of antisymmetry. If I put C as 2, the second one is 0. Now I can write the curvature to form R12 is d omega 1 2. which, and d omega 1 2 is this, is here, and the second term is 0. So this is my curvature 2 form. Okay? I can read out the Riemann tensor by this relation. All right? And these are my Riemann tensor components. The Ricci tensor comes from contracting the two indices. This was taught, no? Ricci tensor?
No,
Not yet.
we just finished
Riemann tensor, okay. Given the Riemann tensor, if you contract the first and the third index, you get the Ricci tensor, the second rank tensor. If you contract both the indices of the Ricci tensor, you get the Ricci scalar, which turns out to, so these are the Riemann tensor components. The Ricci scalar is just 2 by r square, and very nice, you get the Gaussian curvature of a two-sphere. There is only one independent curvature really of a two-sphere, and that is the same as the Gaussian curvature. So it's very reassuring that Riemann's expression for the Riemann tensor and here the curvature 2 form correctly, there's a reason why there's this factor 2, ignore it. We get the fact that the curvature of a two-sphere is basically 1 by r square, as Gauss had done. So I'll stay here for a moment, have a look at it, see if you want to ask me anything. Do you get some idea how you calculate curvature 2 form components? And Farus, you get some hang of it? Yeah? You can do this for anything now, for any situation, not just 2D. Now we want to see this in a real life general relativity kind of situation. Sub 4-dimensional space-time. You have some past background with Robertson-Walker space-time, most of you? No? So so here we have a two-sphere, a homogeneous and isotropic universe. The spatial surfaces are surfaces of constant curvature. They can be flat, where the curvature is 0. They can be open, where the curvature is negative, or they can be closed, where the curvature is positive. And positive curvature is the 3-sphere. Yeah? So I want to show you, just demonstrate the same calculation for an expanding closed universe. So what's happening? A 3-sphere is expanding in time, and you can write the metric for it. And if you ask me something, if you want to say anything about the Robertson-Walker metric, or isotropic homogeneous universe expanding in time. So we want to take the case of the closed universe. I have been too lazy to sit down and type all these equations myself. So please pardon me, I just took the screenshots from Misner-Thornwheeler, chapter 14. Curvature computed using exterior differential forms for the, what is the Friedman metric? ds square equals minus dt square plus the scale factor a square t times bracket d chi square plus sine square chi into d theta square plus sine square theta d phi. This you can see is the line element of a two-sphere. D theta square plus sine square theta d phi square is the line element of a unit two-sphere. If you have a three-sphere, the line element is d chi square plus sine square chi. You have three angles now, theta, phi and chi. This chi is also an angle. Okay? Parisi, you are lost. Are you okay? You okay? Right? So this is a three-sphere. Angles chi, theta, phi, and my space of this universe is a three-sphere, and the three-sphere is expanding with time. So I have a scale factor a of t, which measures the stretching of the three sphere, and because it is space-time, there is also a time coordinate, so minus dt square plus. So, this is visually not difficult. An expanding three-sphere metric looks like this. I want to do for this fellow just the same thing that we did here for the two sphere. Very straightforward, just 4 space-times in dimensions instead of 2. This represents a space-time where each constant t hypersurface is a 3-dimensional hypersurface of proper circumference 2 pi at. So, this is a hypersphere. You go around it once, imagine, you visualize, it's a hypersphere, you go around it once, you can make a circle that still has a simple expression for its circumference, that is 2 pi, ignore that. An orthonormal basis is easily found in this space-time. So, this is straightforward. I write it in terms of basis 1 forms, now denoted by omega instead of e. Omega t hat is dt, omega chi hat is a d chi, omega theta hat is a sin chi d theta, omega phi hat is a sin chi sin theta d phi. Is this okay? Yeah? Not difficult. So far so good. We are just going to repeat these same steps. Calculate the connection 1 form. We already have this basis, right? We have this basis just like here. Where did I write the basis? Here. So, we have defined the basis. Now, we do the rest again with 0 torsion. Okay. This just says that the connection 1 forms are antisymmetric. So, there are only 6 1 forms to be found. Yeah? In 4D, second rank antisymmetric tensor, only 6 components. Turn to the second basic, this is the Cartan structure equation. The game now is to guess a solution to this equation. Yeah, this is the first Cartan structure equation in which the omega and thus the d omega nu are known, and the connection 1 forms have to be found out, the basis 1 forms are known. So, good to use guesswork. So, omega t is dt, obviously d of omega t is 0, and what this is d of omega t is minus omega t mu omega mu. Okay. So, d omega t is minus t k. K is for spatial components 1, 2, 3, because if you put mu as time direction, it will vanish. This equation should be satisfied by having omega I k proportional to omega k, or in more blah blah, or simply omega I k equals 0. If you so he's doing guesswork. You can do it without guesswork also. If omega I k is 0, this equation will be satisfied. The omega I k is a connection 1 form. It's a number. Acting on a vector, it will give me a number. But it can vanish, just like some gamma components, Christoffel symbols can vanish. So, what does he say? Proceed, what is the next? No, something went wrong. Yeah, this is what I was, from that slide, this proceed, sometimes MTW is very witty. Proceed not looking for trouble until some non-zero omega is required. So, he puts omega k as 0, okay. Omega t k he puts as 0. So, you have found, unless you run into a contradiction, you work with omega t k as 0. And then similarly work out omega d omega chi. This is the Cartan structure equation, okay. And now what do? I know what I know dt, I can write dt is just here, dt is just 1, d omega, dt is omega t, d chi, how to find out d chi? Where was d chi? D omega chi, when you do a differentiation, the scale factor is a function of time. Give you a dot dt wedge d chi. If this is your omega chi, d omega chi is a dot dt wedge d chi. Right. Right. D omega chi is a dot dt wedge d chi, and then you write it in another way. This is your Cartan structure equation. You have this d chi on the left hand side, you have these terms on the right hand side. Just compare and simplify things. And finally you can guess, these are connection 1 forms, so the notation is very bad. Omega with 1 index are basis 1 forms, omega with 2 indices are connection 1 forms. But by looking at this fellow, you can work out these, and similarly take omega phi, do d omega phi, simplify, put it in the Cartan structure equation. This is what has been done. And so on and so forth. This is my final result for the connection 1 forms. I can go through this in more detail, but please tell me if you get the hang of it. Do you get the hang of it? Yeah? You have to simply take the basis 1 forms omega, find d of omega, put it in the Cartan structure equation, and work out the connection 1 forms omega a, b, or whatever, and this is it. This is the same information as the Christoffel symbols, gamma. Gamma components can be read off from here by writing this in a basis. Of course, if these hit or miss methods of finding omega do not work easily in some problem, there is a systematic way to solve them. Okay? So you less like in the two-sphere case, once you have calculated the connection 1 forms, you have to differentiate the connection 1 form and get the curvature 2 form. This equation is short enough that one can write out the sum. For example, R T chi, mu is T, nu is chi, R T chi, and write the right hand side explicitly. There will be no T T terms, there will be a T theta term, and there will be a T phi term. Okay? Carry out this differentiation d, so you can verify d of omega t chi is a double dot dt wedge d chi plus a double dot by, so this is what you will get by doing the exterior derivative of this connection 1 form, because I know the formula, I know dt chi. Where did we, this is dt chi, somewhere here, where is t chi? Right, okay, it's written here. The chi will be a k is from k is chi theta phi. So if you know, put k as chi, it will be a dot by omega chi, and do that differentiation, and here's what you get for R T chi. And so we have already got one curvature 2 form. Similarly, you can do, so this one we get same idea, you can find R chi phi and everything and read off the Riemann tensor. It's too quick, but please stop me, say something. I hope you get the basics. The basics are very, you want to say something? Say thoda loudly, please.
The physical interpretation of this, the Christoffel
Okay, Christopher, okay, let's start from the beginning. The metric are potentials, like the vector potential of electromagnetic field. Newtonian gravitational potential, there was one of them, just this phi, phi is minus g m1 m2 by r. Instead of one, there are 10 g mu nus. The gradient, the derivatives of the potentials are the gammas. They are gravitational force, just as you gradient of potential is the force. So there it was gm by r square from differentiating gm by r. Here you differentiate the metric, you get the Christoffel symbol, and they are gravitational forces. They are the analog of the electromagnetic E and B, the field tensor. Differentiate the gammas, you get what is called the tidal force, because gm by r square, if you differentiate, you get the tidal force. What the Riemann tensor does is, it tells that if you have two geodesics, one falling under this force towards the earth, how do they deviate from each other? How do geodesics deviate is measured by the Riemann tensor. If geodesics don't deviate, there is no curvature. Is that what you are asking? Is that okay? So, yeah, sorry, this is getting too much into numerics because I wanted to tell how it is done, but I hope you are clear here. Okay, so if you look, Ms. Nathan Wheeler is very good to look up in this regard. And so please, you get some idea of how curvature and curvature tensor connection, two forms and all can be computed using the language of differential forms. The rest of the time now I try to just give some more insights into curvature. It's good to you get used to it in as many different ways as possible. The many equivalent ways of defining the Riemann tensor. This you have seen, using Christoffel symbols. These Christoffel symbols need not be symmetric. They can have an antisymmetric part. If torsion is present, define the torsion tensor as the antisymmetric part of the Christoffel symbols. Okay? This is the torsion tensor. Here is another definition of the Riemann tensor, non-commutativity of covariant derivatives. This you have seen, right? This you have seen yesterday. If torsion is present, you won't just get curvature, the non-commutativity of covariant derivatives will also pick up a contribution from torsion, where the torsion tensor is defined here. This is another definition. By writing the Christoffel symbols as a sum of the symmetric part and something coming from the antisymmetric part. The first part is the Levi-Civita connection, which is the one that is metric compatible. It is symmetric and metric compatible. In general, you can write the gamma as a sum of the symmetric part plus what is known as the contortion tensor, which is made from the torsion tensor, and in other words, is made from the antisymmetric part of the Christoffel symbols. Okay? If you have torsion present, you can still write the full Riemann tensor as the conventional one. This circle on top says no torsion. And all the covariant derivatives are made using the Levi-Civita connection. So, if torsion is present, the Riemann tensor picks up a correction which is given by this. This is due to torsion. The circle here means that this covariant derivative is made using the Levi-Civita connection. So, this is maybe just lot of maths. I am just trying to tell you, if you can keep this as a record because you have the slides, that what changes take place when torsion is also present. coordinate-free definitions of torsion tensor and Riemann tensor. My notation has changed from theta to t. So this is the same thing as we call theta. Torsion is a two form. It will act on a pair of vectors, in which case it is given by covariant derivative of y along x minus covariant derivative of x along y minus the commutator. This is that so-called Lie bracket. This is a pair of directional derivatives acting, let's say, on some function. Torsion is defined like this in a coordinate free way. The Riemann tensor is defined like this, and if you use a coordinate basis like a capital X's partial derivative with respect to x, capital Y's partial derivative with respect to y, then this commutator is 0. Del by del x del y is equal to del y del x. Commutator will vanish in the coordinate basis, and then the Riemann tensor will reduce to the definition that you saw yesterday, non-commutativity of derivatives. So the torsion involves only first covariant derivatives of vectors, curvature involves first and second. This you did yesterday, symmetries of the Riemann tensor. You did? Okay. So given the above this I am just saying for completeness, the Riemann tensor is antisymmetric in the last two indices. The completely antisymmetric part in the indices beta, gamma and delta vanishes. If you cyclically permute and add them up, you will 3 terms. This we will do in a moment. There is also a differential identity that if you take a covariant derivative and antisymmetrize in these 3 indices, this is the same Bianchi identity that we saw in the differential geometry notation. If the metric is present, there is another symmetry. There is antisymmetry on the first 2 indices. Bring alpha down, and alpha and beta antisymmetric, and together all this then if implies symmetry under pair exchange. If you exchange alpha beta pair with gamma delta pair, that is symmetric. Because of all these symmetries, the original 256 components come down to 20. Why 256? Fourth rank, 4 power 4, that is 256, that comes down to 20 in 4D. And if you want to calculate in terms of curvature forms, only 6. It's a second rank object, it's antisymmetric. The curvature 2 form has only 6 components. So 20 in that sense goes down to 6. You can compute those 6 and then read off these 20, which is what we did in that exercise. Okay, some more interesting things, the many equivalent ways of defining the Riemann tensor. Also the geodesic deviation equations define, this is what you were asking, this is the real physical meaning of the curvature tensor. It measures, this Bhaswati did, no? So we have already seen curvature 2 form as coding the Riemann tensor. Now Newtonian gravitation can also be written in terms, do you appreciate this? No? Right? Well, where does that follow from? You did this weak field approximation for Einstein equations. G00 is phi. So you know the metric. Only G00 is 1 plus 2 phi by c square, all other components. Once you know the metric, you know the gamma, you can calculate the curvature. So you can write Newtonian gravitation also in the language of curvature, which means there is no gravity even in Newtonian gravitation. There is only curvature of space-time. So in that sense, in principle, Newton could have discovered curvature description of gravity, even while staying non-relativistic. But he would have to know the work of Gauss and Riemann or invent it all himself, that absolute space is not absolute really, it has curvature. So that is taking equivalence principle to one higher level. In a little bit surprising how Newton missed it. Einstein realized the same thing that Newton could have realized. Einstein did not need more data. So he's saying that if you non-inertial frames are inertial frames with a gravitational field, and locally the physics is indistinguishable. For this you don't have to know special relativity. Galilean relativity is good enough. All you say, when I free fall in a gravitational field, the laws of physics are that of Newtonian mechanics, as if there is no gravitation. So in other, or he could have said, since in non-inertial frames the geometry of space, no time, space is non-Euclidean, gravity is geometry. So you see, in principle this is doable at Newton's time also. Definition of curvature tensor does not require metric a priori, and this is very interesting. You know this, no? Sum of the angles of a triangle departs from 2 pi when there is curvature. You draw a triangle on a sphere, the sum of the angles is greater than 2 pi. If you draw it on a negative curvature surface like a saddle, the sum of the angles is less than 2 pi. On any curved two surface, the sum of the angles, if you have a triangle delta and the surface has a Gaussian curvature k, you integrate the Gaussian curvature over the area, that is the difference from pi. Okay, no curvature means the integral is 0. If there is a curvature, the total will be more than 180 degrees by this amount. In 2 dimensions, the Riemann tensor is related to the Gaussian curvature and the 2-dimensional metric by this relation. You substitute it in here, do some gymnastics, you will get this result that the Riemann tensor determines how much the sum of the angles of a triangle is different from 2 pi. This is another way of introducing the Riemann tensor. The sum of an angles of a triangle departs from 180 in a manner which is determined by the Riemann tensor, and this you can do on any n-dimensional surface. And if you are on a sphere, then I know the Gaussian curvature is a constant, it is 1 by r square, and then the formula is very simple. If you are on a 2 sphere and you draw a triangle with the area A, the sum of the angles differs from 180 degree by this amount. Okay. Okay, this is the last part. I still seem to have half an hour. We can chat. Okay. Bianchi identities from the 2 Cartan structure equations. So maybe if I go back somewhere, I wrote down what is happening in these 2 equations, the so-called Bianchi identities. I am taking the exterior covariant derivative of theta, and then I have to prove that when I take d theta, d acting on this will give me the curvature 2 form wedge EB. So clearly, when capital D is acting on omega, it will produce curvature. Curvature is the gradient of the connection. Similarly, capital D acting on the curvature 2 form, it turns out it's very interesting, this is identically 0. So these 2 Bianchi identities can be derived by just crunching. So what do I do? This is my first Cartan equation. I will act the exterior covariant derivative on t, the same as theta, just notation has changed. By definition, capital D acting on t is small d acting on t. plus omega AB wedge TB. This is like the covariant derivative. The exterior covariant exterior derivative is the same as concept as the ordinary covariant derivative. This is equal to d times substitute for t. Okay, there is an expression that I have for t, no? Right? I don't think I've written it, not written it here. You have formula for the torsion tensor, which is this one. This is the second term. Use d square as v equal to 0. Do the rest of the differentiation. Fairly straightforward in concept. Substitute this from the first Cartan structure equation and crunch. Okay, finally you will get this nice result that it's very straightforward, it's nothing difficult here, that the covariant exterior derivative of the torsion, this is the first Bianchi identity. Physically, what does it mean? If there is no torsion, it will place a constraint on the Riemann tensor, namely that it is antisymmetric in the second, third, fourth indices, and here also this capital omega is the same as the curvature 2 form. Capital omega AB is the curvature 2 form that I had earlier denoted by R. Okay, similarly you can prove the second Bianchi identity. We have this expression for the curvature 2 form. Take its exterior covariant derivative. It has two indices. So when you have a second rank tensor, if you take a covariant derivative, you will have a partial derivative term and two terms involving gamma. So this is again just acting by definition. D of omega AB is the exterior derivative of omega AB, terms arising from connection after parallel transport. Now compute the ordinary exterior derivative of omega, because I know the definition of omega and I need this, substitute this here and simplify this, the rest of the terms. So this one will be vanishing. Now act D here, namely act D on this, it will give you this. Put it in here, put this in here. And again very straightforward, everything will cancel and this is the result you will find. It again, I mean, I didn't do the maths, it's very straightforward. So this is the Bianchi identity relevant for us in general relativity. What does it translate into? It is like saying the covariant derivative of the Riemann tensor is 0. Written explicitly, it is this relation. The vanishing of the vanishing of the covariant exterior derivative of the curvature 2 form is this condition, okay, and I know how to write this in component basis. This is the Riemann tensor. Omega is this. Substitute for omega in this basis notation, then this vanishing amounts to this object. Let's see what is it. Grad E R A B C D. A you keep fixed, B also you keep fixed. A is fixed, B is fixed. The other three indices are to be cyclically permuted, and that is how what will give you the second and third terms. This is the so-called Bianchi identity on the Riemann tensor, which the Riemann tensor must always obey. This is analogous to, in electrodynamics, dF is 0. F was the field tensor, that was the curvature, dF is 0. And now the analog of the field tensor is now the Riemann tensor. So d omega equal to capital D omega equal to 0 is more like the analog of df is 0 in electrodynamics. Written explicitly, it comes to this, and maybe I will explain a little bit next time. Just as df equal to 0 is related to vanishing of boundary of a boundary, the vanishing of capital D omega, the vanishing of this object is also the same statement as the boundary of a boundary is 0. It comes from there. And finally, in this line, if you make a contraction of indices twice, first you will get you contract A and C, you will get the Ricci tensor. Then you contract the two remaining indices in the Ricci tensor, you will get the Ricci scalar. And finally, this Bianchi identity simplifies to this. This is very famous. This quantity inside these brackets is called the Einstein tensor, where Rij is the Ricci tensor. So Rij minus half Ij R is this object. So this is the Ricci tensor, this is the Ricci scalar, this is called the Einstein tensor. Its covariant divergence is 0. Gik semicolon k is 0. And why is that helpful? Do you know that? Right. Because this Rij minus half Gij will come on the left hand side of Einstein equations. Since the divergence of the left hand side is 0, the divergence of the right hand side should also be 0. T mu nu, the energy momentum tensor divergence is 0, and that is equivalent to conservation of energy momentum tensor. So the conservation of energy momentum tensor is a consequence of the Bianchi identity, which is beautiful. Physics is related to geometry, or you could say that since energy momentum tensor is conserved, whatever you are going to put on the left hand side should have vanishing covariant divergence, and that is so early on Einstein was doing Einstein equations just with Rij. Rij equals Tij on the right hand side. Then he realizes it's not satisfying where vanishing divergence. That is how he put the Ricci scalar term in it, and finally everything looks nice. So you already have the Einstein equations. Rij minus half Gij R equals 8 pi G by C for Tij. Those are the Einstein equations, what you call G mu nu equals T mu nu. And that those are what? Generalized Newton's laws of gravitation to the relativistic case. So this is all for today. It's surprising ahead of time, but either you can leave, have tea, or I would prefer that you talk to me for 20 minutes. I have to still answer your question about the Weil tensor. I will do that by tomorrow. So Rajesh raised a very interesting point. See, the Riemann tensor has more information than the Ricci tensor. Ricci tensor has 10 components. A symmetric tensor in 4D, it has 10 components. The Riemann tensor has 20 components. So clearly the Einstein equations are only about the Ricci tensor and the Ricci scalar. They are not about the full Riemann tensor. The Riemann tensor can be decomposed into two parts. One part known as the Ricci tensor and another part which I will define tomorrow known as the Weil tensor. The Riemann equals Ricci plus Weil, where Ricci is what is entering here. So the Weil tensor is not entering Einstein equations, but if you find the metric by solving Einstein equations, what do we solve these equations for? To find the potential. Given a matter distribution, find the potential, find the forces. That's what we do in Newtonian gravitation also. So here, once you have found the potential, namely the matrix, you can put the metric in the expression for the Weil tensor. Weil tensor depends on gammas, but it is that part which does not enter here. So once you have the metric, you can find the gammas, put it in the Weyl tensor, you will be determined by the Einstein equations, but indirectly. So the Weyl tensor can in principle have a part which need not come from Einstein equations. In principle, you could do that, nothing would go wrong. And for example, gravitational waves have a non-zero Weyl tensor. They have zero Ricci, because if there is no T mu nu on the right hand side, let me the Einstein equations are Rij minus half Gij r equals Tij. Okay? If there is no energy momentum on the right hand side, the left hand side is 0. Rij minus half Gij r is 0. You contract it, it will tell you that r is 0, and if r is 0, then Rij is 0. So in empty space-time, the Ricci tensor is 0. There is only Weyl tensor. So gravitational fields are in an empty space-time. So they have a non-zero Weyl, they have zero Ricci tensor. The Weyl and Ricci have interesting physical implications. So I try to explain better tomorrow to your question, to what extent is the Weyl tensor determined by the Einstein equations. In a homogeneous and isotropic universe, the Weyl tensor is 0. That can be shown. Yeah? Like if the universe is homogeneous and isotropic, you will have a non-zero Ricci tensor, but you will have a 0 Weyl. As inhomogeneities develop, the Weyl curvature grows. So some people have in the past worked with the idea that Weyl curvature has something to do with gravitational entropy. So Roger Penrose, by the way, if you want, you can come for his talk next week. This is precisely what he will talk about, Weyl curvature. That he has a hypothesis. The universe began with the Big Bang, suppose if it did. The Big Bang was an extremely low entropy situation, homogeneous and isotropic. It is 0 Weyl curvature. So, whereas it is evolving to form black holes, which are highly inhomogeneous and very high Weyl curvature. So the Weyl curvature hypothesis says that the universe begins with 0 Weyl curvature and goes to very high Weyl curvatures. At the same time, that's a mystery. Why was the universe starting with 0 Weyl curvature? Who ordered that? Because Ricci and Weyl should both be present, but Ricci is non-zero, Weyl is 0. So Penrose has this theory called conformal cyclic cosmology. No, not many people take it seriously, because seriousness is defined by what is mainstream, and mainstream is lambda CDM, etc., with inflation. But Penrose's idea, which he will talk about on not next week, this week, Friday, 4th July, that the universe undergoes cyclic evolutions, maximum size, minimum, like in our mythology, right? What does our mythology say? What do you call it? Not chakras. Cycles. There are cycles of. There are Big Bangs, expand, Big Bang, expand, contract, Big Bang. So this is called conformal cyclic cosmology, which according to him, explains why the Weyl curvature was 0 at every time, why it goes to 0 at the Big Bang. And now he is claiming that there is a confirmation for his conformal cyclic cosmology in cosmological observations. This is not everybody is happy with Penrose's claim. Some giant rings have been observed, 2 giant rings of the order of billions of light years, nearly the same size of the universe. Galaxies are located along a giant ring, and if you see a structure like that, that's troublesome for core lambda CDM, because you're not supposed to see structures of the order of the size of the universe. And Penrose is claiming that if you have a cyclic cosmology, supermassive black hole mergers will give rise to gravitational waves, and somehow gravitational waves from the previous eon of the cyclic universe are causing these rings. I am also curious to see what he wants to say, what is his logic, but he is claiming that these rings are evidence for his theory. Also, what's very interesting is Roger Penrose, 94 years old, and he's nearly blind, but his brain is extremely sharp still. If you talk to him, I mean, Zoom only, but he doesn't travel. He's very sharp. He will know these things 20 times, 100 times better than I understand. So he remembers everything, while curvature, this, that. He doesn't forget. Extremely good understanding of geometry even today. So it's always fun to listen to him. So you are most welcome. All right, please say something. I'm the only one talking. Right, In general relativity, gravity potentials are the metric. Newtonian gravity is a special case of general relativity, so that is also describable using a metric. The metric in Newtonian gravity has only essentially one non-zero component, g00, which is 1 plus 2 phi. So you write the metric for Newtonian gravity, calculate the gammas, calculate the curvature. Physically, the point is equivalence principle holds in Newtonian gravitation also. That is the essence, right? That you agree, no? Only thing is, in a free fall in Newtonian gravity, the laws of physics are that of Galilean relativity. They are Newton's laws of mechanics. They are not special relativity. But equivalence principle is there, and the same interpretation that gravity is equivalent to non-inertial frames is holding there also. So gravity is the curvature of space, not space-time, of space, even in Newtonian mechanics. Does that help? Yeah? Because you have a G naught knot.
Maybe I missed it, but you said, the Einstein equation doesn't have all the components of the Riemannian tensor. So those are not independent, or how are they determined?
The Weil tensor. Right. So take the Riemann tensor, write it as Ricci tensor plus Riemann tensor. Weil, sorry. Start with the Riemann tensor equal to decompose Ricci tensor plus something called the Weil tensor. 10 components in Ricci, 10 in Weil. Total 20 for Riemann. So solve Einstein equations by constraining the Ricci tensor like this to find the metric. Take that metric, put it in the Weil tensor, so you get a solution for the Weil tensor.
That sort of implies they're not independent. Once you have the
if there is matter sources, they will tell you what the Weil tensor is. But there's a part 2 to that story. Suppose matter is 0, no empty space-time, no matter, T mu is 0, then Rij is also 0. So that I call Ricci flat. But Rij doesn't mean 0 doesn't mean that the curvature is 0, because the Weil tensor is still there. That could be getting determined independently, let's say by presence of gravitational waves. If gravitational waves are present in an empty space-time, I am not using this equation at all. So gravitational waves will have a non-zero Weil curvature.
So there should be two equations here, when Weil equation.
Yeah, very good. What determines while? So I still have to Raj. That's what Rajesh was asking yesterday. What determines while? You are saying what is the source term for while?
No, not just that, but this is not the complete description of gravity. You need the while tensor too. Especially if
The metric determines while if matter is present. If there is no matter, then the while is not constrained. Yeah, I think I am not giving you the full answer. I told Rajesh I'll think about it, get it clear in my head, so by tomorrow I can say something better. Oh, in the chat, sorry. Okay, two in the end, ऊपर भी है? Just two, okay. In the curved two surface Riemann tensor, I saw there are two metrics, G mu nu. Could you tell me how does that come in the, okay, maybe just I'll come back to this in a minute. One moment. I think the question is about this thing. If I understood correctly, this is a two-dimensional surface. This is the expression for the Riemann tensor. You can prove this. Here is by two metrics. It's quadratic in the metric, no? The Riemann tensor is quadratic in gammas. Hence, it is quadratic, bilinear in the metric. Nothing surprising here. Okay, now next question. What are the consequences of gravitational entropy? Anybody you want to say something? How do I understand this question? Consequences. Huh? What? Yeah, the black holes have an entropy. That we are certain of, because there is this black hole area theorem which tells that when two black holes merge, the surface area always increases. So area behaves like entropy, and if you treat a black hole quantum mechanically, then you can show that it has a finite area which is finite entropy which is proportional to area over h bar. In the classical limit, when your h bar goes to 0, the entropy goes to infinity, because essentially everything is going in, all information is lost. But because quantum black holes emit Hawking radiation, they have a finite entropy, dq equals TdS. The amount of mass or energy lost is proportional to the Hawking temperature of the black hole and also to the entropy, which is proportional to the area. So definitely we can say black holes have entropy. So then arises a very interesting question, which is what is being asked here. Suppose you have inhomogeneous material bodies like stars or planets are here. This is not a black hole, but this is still an inhomogeneous gravitational field. Does it have entropy? I think that question is not answered to the best of my understanding. It's an open question, which is what Penrose is interested in. If the universe is homogeneous isotropic, while curvature is 0. If it is inhomogeneous, the while curvature is non-zero. Is it that the while curvature is a measure of gravitational entropy? It is for the black hole case, but when there is no black hole, how to define gravitational entropy, say in terms of the while curvature? We don't know. There's a lot of work that has been done, but there's no final answer. So there's a simple answer for black holes, quantum black holes. You're right. So I should say that quantum black holes have entropy. Classical gravitational fields Whether they have entropy, we don't know. I don't know. Black hole treated according to the laws of quantum mechanics. That's if a black hole is emitting Hawking radiation, it will have an entropy. Right? Maybe Ashmita talked about it. Because if you are emitting like a black body radiation, your entropy is just dq by t, where dq or q by t roughly. That's why the black hole has an entropy which is proportional to the area, mass square.
The motivation was from Bekenstein's
Yes. Because the black hole area is always increasing during black hole mergers. Area is already showing signs of being something like an entropy, and Hawking radiation puts that on a firm footing. So whether classical gravitational fields have entropy, whether if you quantize them, there is some entropy, these things are not clear, they are not understood.